Hello everyone, this is Jesse Smith from Maryville College, and today we're going to look at geometric series. In this section I'm going to introduce what the geometric series is. We're going to try to figure out when does the geometric series converge, and in the process of answering that question we'll actually figure out the sum of a convergent geometric series. So we'll see what that formula is, and we'll see how to apply it, and then we'll wrap up the section with a punny section, some sum rules. So recall, what does it mean for a series to converge? We say that an infinite summation, or an infinite series, k equals 1 to infinity, a sub k converges to a finite value L if and only if the sequence of partial sums, Sn, converges to L, as n gets larger and larger. S sub n here is the sum of the first n values of the summation. So instead of going 1 to infinity, we simply go up 1 to n and stop. So if I want to figure out S sub 10, instead of adding up infinitely many things, I simply add a1 plus a2 plus a3 all the way out to plus a9 plus a10. That would be the 10th partial sum. I can go and find S sub 11 by adding on a sub 11. I can find S sub 12 by adding again onto that a sub 12. As n gets larger and larger, I get a better approximation of the infinite summation. So the limit of S sub n should be, and it is by definition, the summation from k equals 1 to infinity of a sub k, or the infinite series. We will say that the infinite series diverges to infinity if and only if the partial sums diverge to infinity, and that the infinite series diverges to negative infinity if and only if the partial sums diverge to negative infinity. This definition can quickly be modified if we start out at k equals 0 or any other starting number on the bottom limit of integration. A geometric series is a series of the form k equals 1 to infinity, ar to the k minus 1, where a and r are both fixed non-zero real numbers. By rearranging the terms slightly, I can also express the geometric series in a more common notation, k equals 0 to infinity, ar to the k, as you see expressed here. If you cannot see that these two summations are equivalent, the way you can convince yourself of this is to expand this side and see what the summation is, and expand this side and see what the summation is. You should get the same thing in both expressions. Thus, they are equal. Our first order of business here is to actually determine when a geometric series converges. In order to do that, we look at the partial sums and see if we can't figure out what the partial sums are doing. So S sub 1, I'll simply take the first term in the series and not add anything to it. That would be ar to the 0, or just a. S sub 2 will be the first two terms in the series added together. So it's just ar sub 0 plus ar to the 1, which simplifies to a plus ar. Can you figure out a formula for S sub n? If you expand that, you get S sub n is equal to ar to the 0 plus ar to the 1 plus ar2 all the way out to plus ar to the n minus 1. I want to actually find a much more compact formula for S sub n. So I'm going to do some algebraic manipulations to this. What I'm going to do first is to multiply both sides of that equation, equation 1 here, by r. On this side I'll just get rsn, but on this side I can distribute and I'll get ar plus ar squared all the way out to ar to the n using rules of exponents. Doing a little bit more algebraic manipulation, if I subtract these two lines from one another, it's almost tax season, so let's pretend like we're doing taxes. Let's subtract line 2 from line 1. If we do that, on this side I'll get Sn minus Rsn, and on this side I get a lot of cancellation. Notice these will cancel when I subtract. These two terms will cancel when I subtract. The ar2 minus ar2, or the ar squared minus ar squared will cancel. There's an ar cubed and an ar cubed here that will cancel. All that will survive is the first term here. There's nothing down here to subtract off to get rid of it. And this term, as there's nothing up here that will be positive when I subtract this away, that it will go away. So I'll simply get a minus ar to the n when I subtract line 2 from line 1. Now, continuing with some algebraic manipulation, I can factor the s sub n out of the left-hand side. I can factor an a on the right-hand side. Divide both sides by this 1 minus r because I'm looking for a nice compact formula for s sub n. I will get s sub n on this side, and over here I'll get a times 1 minus r to the n, all divided by 1 minus r. I'm going to rearrange this in a strange way, and you'll see why shortly. I'm going to put the a over the 1 minus r in front and put this at the end. This is legal when r is not 1. If r is 1, I would be dividing by 0. So this move to this move is only valid if I'm not dividing by 0. So r is not 1. This is true. When r is 1, it does not work. We will handle that case separately. So we now need to take the limit as n goes to infinity of Sn. This part of the formula does not have an n in it. So this is a constant as n is changing. So if we're taking the limit as n goes to infinity of this thing, this can be pulled out in front using the constant multiple rule for limits. Then we're left with taking the limit as n goes to infinity of this. But using the difference rule for limits, it would be the limit of this minus the limit of that. Well, the limit as n goes to infinity of 1 is 1. So we really just need to figure out what is the limit as n goes to infinity of r to the n. If we can answer this question, then we're good to go. We'll notice that r is not 1, so we don't need to stress about that. I can only do the algebra on the previous slides as long as r is not 1. We'll come back to that later. But let's look at all the different graphs of r to the x. This is an exponential curve. I've graphed several of them below in different colors here. This is 0.2 to the x, this is 8 to the x, this is 2 to the x, a few of them there. What you can notice is that when r is less than 1, you'll have a decreasing function, and when r is bigger than 1, you'll have an increasing function. And when r is less than 1, you'll be converging to 0 at infinity, and when r is bigger than 1, you're going to be diverging to infinity. This will also be true if you're negative. So if you look at a negative r, I don't have them graphed here, but if you look at a negative r between 0 and negative 1, you'll get a curve that's alternating, but it's still decreasing down to 0. And if your r is below negative 1, the sequence will alternate and will bounce back and forth between a really large positive number and a really large negative magnitude number. In that case, the series would diverge. If r is exactly negative 1, we'll just get the alternating sequence negative 1 and 1. Think about negative 1 to the n power. That's just going to bounce back and forth between negative 1 and 1, so it will diverge. From what we've looked at, we know that if we're looking at the limit as x goes to infinity of r to the x, it's going to converge to 0 if the absolute value of r is less than 1, and I'm not looking at r equal to 0. And it's going to diverge if the absolute value of r is bigger than 1, and it will diverge if I'm looking at 1 or negative 1. So I can actually change this line to simply be the absolute value of r is greater than or equal to 1. Well, if the absolute value of r is less than 1, again, that means that r is between negative 1 and 1. I can take the limit as n goes to infinity of s sub n. This is the formula we derived from before. This constant multiple can come out in front of the limit by properties of limit laws. The limit of this difference is simply 1 minus the limit of this, but we saw from our graphs that limit will be 0. So I simply get this number times 1, so I simply get that constant multiple in the front, a over 1 minus r. Is bigger than 1, or if r is negative 1. From the previous slides, we saw that the limit as n goes to infinity of this will diverge. Thus, this limit will diverge, and so the entire limit diverges. So what remains now is to consider the case when r equals 1. Our original algebra does not work, so if we return to the original partial sums, we've got this expression, because our r's are 1, we are simply doing a plus, that's simply n times a. A is assumed to be a non-zero real number, so as n goes to infinity, this will go to infinity or negative infinity, depending on whether a is positive or negative. In other words, this sequence will diverge, so if r is 1, our series diverges. Here's the big slide. The geometric series, the sum from k equals 0 to infinity, ar to the k, where a is not equal to 0, is a real number, and r is a real number. This will converge or diverge in the following cases. If the absolute value of r is less than 1, it will converge to this number, a divided by 1 minus r. And if the absolute value of r is greater than or equal to 1, it will diverge. So let's see some examples of applying this. Consider the series 1/9 plus 1/27 plus 1 over 81, etc. If I want to figure out a formula for this summation, to notice that it's a geometric series, I notice that to go from here to here, I multiply by 1/3. And to go from here to here, I multiply by 1/3. Another way of figuring out what I'm multiplying by to get these numbers is to simply take this number and divide it by 1/9. I'll get 1/3 from my calculator. And if I check this number divided by this number, I'll also get 1/3. So I know that the multiplier at each step is the same to get the next term. So it's a geometric sequence with an r of 1/3. So I'm putting my 1/3 here, being raised to the kth power. Then my first number is my a term. My starting term is 1/9. So here a is 1/9, r is 1/3. To figure out if the sequence converges, I simply look at r, take its absolute value, and see if it's less than 1. The absolute value of 1/3 is 1/3. 1/3 is less than 1. So the series does converge. I can plug a and r into the formula to actually figure out what the series converges to. So here a is 1/9, r is 1/3. R, an absolute value, is less than 1, so we do converge. I can plug a and r into the formula. I get 1/9 divided by 1 minus 1/3. That will work out to be 1/6. If I look at this series, the sum from j equals 0 to infinity, 42 times 1.1 to the j. This is a geometric series. A is 42, r is 1.1. In this case, since the absolute value of r is bigger than 1, the series diverges. Here, we have a geometric series with a is 11, r is 0.5. The absolute value of r is 0.5, which is less than 1, so the series does converge, and it converges to a divided by 1 minus r. In this case, that would be 11 divided by 1 minus 0.5, which will be 11 divided by 0.5, which is the same as 11 times 2, or 22. One final example, the sum from k equals 1 to infinity, 42 times 0.2 to the k minus 1. Remember, this is just another way of representing the geometric series. We can start out at 1 if in the exponent, instead of having k or whatever this index is, we have k minus 1. Then this is another way of expressing the standard geometric series. Here a is 42, r is 0.2. The absolute value of r is 0.2, so you can plug a and r into the formula and get the value to which it converges. That formula is only valid if the absolute value of r is less than 1. So in example 2 on the screen, the formula a divided by 1 minus r is not helpful. That doesn't give you the value to which the series converges, because in number 2 we actually diverge. Finally, we'll close with some sum rules. This is the sum, difference rule, and constant multiple rule for convergent infinite series. And I put convergent in bold, and that's important. This rule does not apply for divergent series or for general infinite series. We have to know beforehand that the two pieces that we're working with are convergent. So if I have a convergent series AN and a convergent series BN, where the first one converges to some number capital A and the second one converges to some number capital B, then I also know that if I add the terms, that will produce a new convergent series, and it will actually converge to the sum of the series, which will simply be capital A plus capital B. The same thing is true for subtraction. For an infinite series that converges, if you multiply every term by a constant number k, you can actually factor that k out in front, in which case you're going to get k times, in this case, capital A, because I'm assuming that the infinite series an converges to capital A. These rules only work for convergent series. This is helpful for me because I can find sums of more complicated series. So if I look at this weird example here, I've got the sum from k equals 1 to infinity of a beautiful looking fraction. But if I work with that fraction, separate it to the difference of two fractions, so I get 3 to the k minus 1 divided by 6 to the k minus 1 minus 1 over 6 to the k minus 1. All of this is in the summation. All of this is still in the sigma notation. I can then simplify this. I can bring the k to the 1 outside, and I'll get 3 over 6 on the inside. That simplifies to 1 over 2. Bring the k minus 1 back in using laws of exponents. It would simplify to this. 1 over 2 to the k minus 1. This is 1 over 6 to the k minus 1. I'm going to split this up as two different series. And this will only work if, when I get to the end, I get a finite number. And I get that both of the two series converges. So this step is only valid if this works out to be a convergent series and this works out to be a convergent series. If, after this point, I get divergent along the way, I get infinity or negative infinity, or that the series doesn't exist, I have to go back and ignore this step. This step is actually invalid. I have to return here. I can only do this if this works out to be a convergent value and this works out to be a convergent number. With a little bit of inspection, you can see that this is actually a geometric series. This is the same as doing 1 times 1 over 2 to the k minus 1, or if you rewrite it so that it looks like the standard geometric series, 1 over 2 to the n. The same thing is true for the second series. So that first series is a geometric series with a equals 1 and r equals 1/2. And the second is a geometric series with a equals 1 and r equals 1/6. Both of those have a r of absolute value less than 1, so they both converge. This tells me that this move was valid. I can then plug those a's and those r's into the formula for the sum of the geometric series, work them out. I get 2 minus 6/5, simplify. I get that this series does converge, and it converges to 4/5. So I hope this gives you a good idea of geometric series, when a geometric series converges, why does a geometric series converge when the absolute value of r is less than 1, and how to use that formula when it converges. Have a great day.